Okay, I think most people are here. If some of you see people that are not here that need to hear this, then please communicate the message. So just a reminder, tonight there's school dinner at 8. The place is there. The address is on the website. So TMS, I don't know, the website. So yeah, please be there on time. We'll announce the poster winners. So regarding the posters, there are a few poster tubes, probably with posters inside them, that are there. If it's yours, please take them, because the people that work here want them out. If not, we will burn them to as a sacrifice for good results. You don't do that? Oh, okay. Surf class, so the time is 4, but you have to be there at, maybe 3:30. I think Maya wants you to be there at 3:30, so please be there at 3:30. Bring towel and sunscreen. It gets pretty hot in the water, so do that. And maybe sandals, I don't know. Class, just think and bring the thing that you need. And I think that's all what I need to say. I think, Reyes, I don't see her. Posters, I already said it. Okay, good. So then I'll let Ming continue her lectures. Last reminder, please ask questions. This is for you. It's not for we as organizers and speakers, we're also interested in the topic, so we ask questions, but this is for you. So please ask questions, interrupt. Just, if you're shy, then grab them later and just ask questions. If not, you won't learn.
With that, I will continue. I'm also very shy, but I understand. But I will try to speak slower and look at you in this process too. Okay, so just to continue, so for the second part, I'm going to talk about using ARPAS to study some flatbands in bulk materials. And this was the outline I ended with an hour ago. So we're going to do this in 2 parts. First, I'm going to talk about a couple different lattices that we have encountered and other people have also studied that would produce these geometrically frustrated flat bands. And then for the second part, I will show you some of our attempts at looking for materials with flat bands close enough to the Fermi level, and also that systems that exhibit magnetic order. And so, we haven't done this for twisted materials, but we can try to learn something from, in bulk materials, what are the role of these flat bands for magnetism. Okay, so here we go. Okay, so since Stephen has already given a complete introduction of this, this is easier on my part. He talked about the Kagome lattice, and of course, he's also mentioned that in the materials that we have, there's actually a vast number of such lattices that can give you flat bands. So this is a very nice catalog work that shows some of the common ones, like Kagome lattice, pyrocore lattice, Lie lattice, bipartite and split, so on and so forth. And in real materials, you can actually see DFT calculations showing flat bands near the Fermi level. Okay, so cool. So this is what we wanted to study, and I'm going to tell you about 3 such systems that we have sort of looked into. And I'm going to go really quick on the Kagome since this is already introduced, but just to remind you the 3 key signatures in the electronic structure that arises out of this lattice. So the most important one is the flat band, which if you tune your chemical potential to be in the flat band, then at least one of the ground states is this Stoner itinerant ferromagnetic order that arises because of large density of states. And then we also have the Dirac cone, and then if you incorporate spin-over coupling, that becomes gap, gains barrier curvature, and then you can have anonymous Halls. Stephen's also giving you examples of this. And the third one is this pair of magical Van Hove singularities that will give you a divergent density of states in 2D. And then when you tune your chemical potential to be there, then you get this idealized Fermi surface that has 3 pairs of parallel sheets that would give you a nesting condition. And then from this, one would expect to see a charged water that has, in plane direction, has 2 by 2. So these are the 3 key predictions associated with a Kagome lattice. So this is a sort of a view of some of the systems that have been studied in the past couple of years, organized by phenomenology. So as we have heard, there's superconductivity, CDW, magnetic order, and these are the various systems. And I highlight in red the element that forms the Kagome lattice, and you can see that they expand this role in the periodic table. So the symbolic materials, this is one way of tuning them. And I'm gonna show the way this affects the band structure. So I know this is a very busy spaghetti plots, but if you sort of stare at it for 5 minutes, you will start to see features that look somewhat like this tight binding calculation of the flat band plus the 2 dispersive bands, right? That's the blue things to highlight, and then the other important thing is where the Fermi level is, right? So if you go from system to system, if you look at the vanadium-based, both the vanadium 135 and the vanadium 166, the Van Hove singularity is at least one of them is close to the Fermi level, right? And these are the systems that, as we have heard, exhibit charge density wave orders. And then you keep going, and for the iron-based and also the manganese-based over here, if you calculate the DFT for the non-magnetic order phase, you will see that the topological flat bands is basically right at the Fermi level. And I'm going to talk about this in a little bit. So if you keep going, this is maybe one of the more recent members. This is a chromium-based 135. It's isostructural to the vanadium 135. And in this system, the chromium is in between vanadium and manganese. You can see the flat band is also in between these 2 cases. The flat band is closer, but not yet quite at the Fermi level. And this is also a very interesting system that's starting to give us phase diagrams that look like the cuprates and so on and so forth. Anyway, so I'm going to talk about this at the very last end of this. So you can see that effectively we can use this doping to tune in bulk, which controls not only the filling, but also the strength of the correlations in these materials. That's all I'm going to do for the Kagome for now, because it's already been introduced very well. I'm going to next talk about if you go from 2D to 3D, and I think Stephen has also talked about this 3D pyrocore lattice. I'm going to present them, and I think argue that this is categorically a different category, a different system of materials than the 2D Kagome system. Okay, so pyrocore. As we have learned from the candidates for quantum spin liquids, we know that the one way to go from 2D to 3D is to go from Kagome to pyrocore. Essentially, Kagome is made of these corner-sharing triangles. Pyrocores are made of corner-sharing tetrahedra like this. And there are ways you can cut through a pyrocore lattice that would expose these Kagome planes. So if you cut along the 111 direction, you can trace out this is the Kagome. This would look like a Kagome layer. And there are 3 ways to cut this. So this shows you 2 of them. So why would this give you flat bands? It turns out that if you calculate the linear amplitude, there are 4 sites associated with each tetrahedra. The site which is not contained in the Kagome layer, that site has 0 amplitude, which means there's no hopping. Hopping is quenched even in the vertical direction, perpendicular to the Kagome planes. So what this means is essentially, from a tight binding perspective, we can consider the pyrocore lattice as essentially 2 decoupled Kagome planes. And if you consider nearest neighbor hopping, the tight binding will give you 2 copies of flat bands, and then 2 dispersive bands. So this is what you would get, a flat band in 3D. In addition, there's some interesting things here that you would end up with a triply degenerate point and the gamma point, 2 flat bands and the dispersive band, and then you will have a Dirac nodal line along some path of the momentum of the Brownian zone. Okay, so this is what happens without considering Spermer coupling. If you put in Spermer coupling, there are different ways of gapping this. So you can have situations where the gap appears between the 2 flat bands and the dispersive band, or between the 2 flat bands. But in both cases, you will end up with a doubly degenerate point, the gamma point, associated with the flat band. The second thing that happens is that the spin-orbit coupling will also gap this Dirac nodal lines. It will gap it everywhere except strictly at the X point of the Brownian zone. And what you notice is that actually every single band crossing, as long as your band crosses the X point, it will be a gapless 3D Dirac point. And this is something that's special for the pyrocore lattice. And the reason for this is that there is an intrinsic non-isomorphic symmetry associated with the pyrocore lattice. So how do you see that? So if you remember the construct that Stephen showed about the relationship of the Kagome lattice to the honeycomb lattice, you can do kind of like a similar thing for the pyrocore lattice. And so these are the tetrahedron for the pyrocore lattice. And then if you consider the middle of each of these tetrahedron, those sites will give you a diamond lattice. So just like you end up, if you do this kind of thing for the Kagome lattice, you end up with a honeycomb lattice, right? So it's easier to see this non-isomorphic symmetry in the diamond lattice. If you follow this green screw thing, you will see that there is a 4-fold in-plane rotation together with a quarter translation along the c-axis. This will give you the screw axis, screw operation. So this is the non-isomorphic symmetry. And theoretically, it's already known in the diamond lattice, you have this non-isomorphic symmetry that will give you this gapless 3D Dirac point. So this is something that's associated with it'll map back to the pyrocore lattice. So the key point is that there are 2 signatures in the electronic structure associated with the pyrocore. You end up with flat bands, which are flat, with quenched hopping in Kx, Ky, and Kz, so that's why we call it 3D flat band. And then you also have all of the band crossings at the X point in the Brownian zone. Every single band crossing, as long as the band crosses, it'll be a 3D gapless Dirac point in the presence of SOC. So we discussed this in this paper. Also, I just want to highlight Joe Czakowski's group also recently published a Nature paper talking about these as well. So this is also a very good reference to look up this kind of thing. Sorry, these are the experimental results, but theoretically this has of course been known. Sorry, I should have put some references of the theory work before our experimental works. Okay, all right, so how do we see this in real materials? We just happen upon a material. One of the first that we happen upon is this compound cerium ruthenium-2, which belongs to this Lavis phase that Stephen also talked about. And I just want to give credit to Chen and Seti, who is a theory postdoc working with Timel's group. Until recently, he's starting his own position, Iowa State, very soon. And so he was the first one that told us about this pyrocore lattice and recognized that this material, even though it has a certain direction that looks like a Kagome, but really it's dominated by pyrocore physics instead of Kagome. And then Jianwei is our postdoc who really did the experimental aspect of this. How do you see that? So cerium ruthenium-2 looks like this, the crystal structure. The ruthenium sublattice forms the pyrocore right here. So this is what it looks like. So we started to measure this, and this is a cubic system. And along the way, we also got Jonathan Dellinger interested in looking at this band dispersions. So he did this whole series of calculations just to track what happens to the pyrocore flat band as you add in the cerium. So this is DFT calculation. First, he calculated just the pure ruthenium pyrocore sublattice, and these highlighted in green are the flat bands associated with this destructive interference in 3D. And then next step, he added in the lanthanum, which it's basically the same structure, but without the Fe electrons. And you see the evolution of the pyrocore flat bands, captured here. And then he replaced them by cerium, and then eventually added SOC, so that you can trace that these bands that you calculate, if you calculate DFT for this guy, these are the bands that originate from the pyrocore flat bands associated with the ruthenium sublattice. There are some bandwidth that's gained, but there are portions that are still flat, and experimentally we look for those. And so this is a heroic effort. You can cleave like 30, 40 crystals, maybe get one good regions to measure. This is what we do as experimentalists to try to find the interesting stuff. So we did measurement, and you can see portions of a flat band with a peak here, here near the Fermi level. And then the second feature is that if you look for the direct points at the X point, you can see features that are direct points here, which is protected by this non-isomorphic symmetry. And just also see reference of this calcium nickel 2 material of the same structural family from Zhou's work. Okay, so this is great. It sort of suggests that pyrocore indeed can give you flat bands, but we're not as amazed by the fact that some of this flatness gets hybridized by the other sublattice. So we try to look for other materials that could give you a better flat band. So the next one we encountered is a spinel material. So it has copper, vanadium 2, sulfur 4. It's quite complicated, but if you strip away everything else, leaving the vanadium, you see the vanadium sublattice forms this pyrocore lattice. Why is this better? So we figured out that if you look at the chemical environment of these different things, for the copper tetrahedron, it's actually fully filled. And then it's the vanadium, which is partially filled in the T2G orbitals. So this suggests that this could be very promising because the copper and the sulfur states may be farther away from the Fermi level, leaving behind the low energy electronic structure dominated by the vanadium sublattice. So this is something that's worth looking into. You can see that in the DFT already. So in the DFT density states, all the stuff near the Fermi level you can see is all vanadium. The copper are farther away. And you can see that here is this pyrocore flat band, which is associated with the T2G vanadium sublattice. So we started to look at this, but notice that this position of these flat bands are half EV above the Fermi level. Experimentally, what we saw is actually very striking, which is that you can see that there are these extremely flat band right at the Fermi level. If you don't see that very well with the color maps, what you can do is look at a bunch of the vertical energy distribution curves right here, and you can see that these sharp peaks are the flat band right at the Fermi level. So we actually image these, and we have additional data that shows that this thing is flat in all three directions, Kx, Ky, and Kz. But there's a puzzle, because if you remember from DFT, this thing is half EV above the Fermi level. Why do we see it at the Fermi level? Which is kind of interesting. So if we look farther out in the band structure, we notice that if you stay away from the Fermi level, all of these features actually have reasonable agreement with DFT. So it turns out these are the copper sulfur bands farther away from the Fermi level. It's just the stuff near the Fermi level are not match well with DFT. And this immediately reminded us of the iron nictide stuff that we worked on earlier, suggesting possibly there's some sort of orbital-dependent correlation effects that could be missing in the calculation for the vanadium sublattice. So what can we do? We talked to Timel, who's next door. So basically, they did a tight binding fit of the vanadium T2G orbitals near the Fermi level. And then when they crank this through the slave spin calculations, incorporating equivalent interaction U, And Hans J, they can see that they can renormalize the flat band closer to the Fermi level together with all the other dispersive states near the Fermi level. So you can see the mapping is actually much better to our data after the incorporation of these correlation effects on the vanadium T2G. So this sort of suggests that in this material, we see two effects. One is that, first of all, you have the pyrocore lattice that gave you the destructive interference to produce the flat bands. And then in addition, there's moderate electron correlation effects that further push the flat bands towards the Fermi level to eventually give us this phenomena. So these two effects go hand in hand to give us this flat band near the Fermi level in bulk. And then, from resistivity measurements, we can see that there's a power law which is deviating from n equals 2. It's not quite there for t linear, but it's at least deviating from t squared, as we heard from last talk in Ira's talk. Okay, so that's the second example. So in 3D, we can look at pyrocore. I want to show you one more that is kind of an interesting and very different way of constructing flat bands in bulk. And the difference is that in the previous two examples I showed you, these are fully stoichiometric compounds. You can calculate everything and look at the destructive interference. But there's one more degree of freedom that we can actually utilize to make even more types of these frustrated lattices. And that is the degree introduced by vacancies. So this one we happened upon accidentally, but it turned out to be kind of interesting to look at. To sort of motivate this, you can imagine, suppose you start with a bipartite honeycomb lattice. So you have two species, something like this and something like that. And you punch out some vacancies, and you do that in an orderly fashion. So you end up with something like on the right-hand side. And then you may recognize that this is a repeating unit of this shape, which my student Han named the clover lattice. And it's special because it is a bipartite lattice, which means that the nearest neighbor hopping is always between two different sublattices, number one. And number two is that the number of sites belonging to the two sublattices is different. So if you count up in this unit cell, the red site has 2 per unit cell, and then the yellow site has 3. And immediately, as we learn from Dmitry and Nicola and collaborators here, is that this kind of a bipartite lattice would guarantee that you have a zero mode or a flat band, if you add in spin coupling, this should become this is what you would get from tight binding calculation with the nearest neighbor hopping for this lattice. So there are ways to create this, and why am I telling you this is because we found this accidentally in a material which is actually maybe not so strange. So that's known. So the material is iron, germanium, tellurium, and if you work in the 2D magnetic materials, you know that a couple years ago, this is one of the class of 2D metallic van der Waals ferromagnet materials discovered. It belongs to a large family of this, where you have van der Waals stacks of van der Waals slabs, and you have, depending on the different amount of iron they have different Curie temperatures, and you can exfoliate them to a thin layer regime, and still retain the long-range magnetic order, which is interesting in its own right for two-dimensional magnetic order. But what I'm going to tell you about today is the third member, which is iron 5, germanium tellurium 2. And it has a TC of around room temperature. This is the Curie temperature. The additional degree of freedom that we have in this member that we don't have in the previous two is this vacancy order. So I know this slide is a little bit complicated, but I hope you can bear with me. I'm going to pull out the essence and sort of tell you what's interesting about this lattice. This is a cross-sectional view. This is a TEM image. So its unit cell is large. It consists of ABC stackings of van der Waals slabs. If you look at one of these slabs, you'll notice this is inversion symmetric. And the inversion center lives between these two blue sites. These are germanium split sites. Everything comes in pairs about that inversion center. You have a tellurium pair. You got 2 iron pairs, so these are all fully occupied. The last remaining pair is iron 1 sites, and if you have exactly iron 5, then between each up and down site, you can only occupy one of these 2. So that's the key thing in this material. And it's interesting that people have realized that this crystal actually can be stabilized in 2 structures. And in one structure, between each up-down pair, it'll randomly choose to occupy the up one or the down one across the crystal. So there's no correlation between which one is chosen. So in essence, this is kind of like, locally it will choose one of them, but on average, you can consider each one being 50% occupied. And you can see that this structure is still inversion symmetric globally. The other stable structure, it turns out, is that the crystal likes to choose like these sites in an orderly fashion. It goes like up, down, and so on and so forth. Right, and this one obviously breaks inversion symmetry, so these have different symmetries, but they have the same number of occupied sites per unit. Okay, so why am I telling you this? Thank you for bearing with me for that slide. The reason is that if you actually look at the slice, the horizontal slice, which actually is affected most by this vacancy order, it is this slice, and this is where the shortest bond actually occurs within the unicell, and that's immediately, you can see that this is the view I showed you earlier. In the in-plane direction, this is the system that's this honeycomb lattice, and this is the one that has this clover lattice. So if we do ARPES on this, you can see they have drastically different electronic structures, and the most important thing is that for the bottom one, where you have the site order, bipartite lattice, you actually end up with these flat bands. You can see pervade like over a large portion of the Brillouin zone. And this one, you don't have those anymore. And we can understand this now because you have destructive interference in this vacancy order phase, but not in the upper one, right? And this is there's actually a way to actually switch back and forth between these 2 in a non-volatile way, but I won't. So this is because the vacancy order actually is much more easily switchable than the whole crystal structure. So this is another advantage of constructing these kind of lattices using vacancy orders. Okay, I'm going to digress a tiny bit because there's something interesting as well associated with the other phase, even though this one doesn't have flat bands, but it turns out at the K point, there are these topological crossings due to the global symmetry. So this is interesting. Just to show you the ARPES results for this. At the K point, there's a band crossing. You see that for all KZ. You see that it's basically a bunch of cuts. You can show this is where the direct point is. If you go left, right, up, and down, there's a gap that opens. So this just looks like a direct crossing. It's kind of interesting to think about because even though locally it breaks inversion, but the global inversion symmetry is protected, and it also has the C3Z. Symmetry and also C2Y. And these together would give you the crossing at the K point. And then we have ABC stacking of the van der Waals layers. This will lead to helical nodal lines around the K point as you go in the KZ direction. So this is actually, these are topologically distinct situations. And so for the bottom one where the inversion symmetry is broken, you actually see the lifted degeneracy here at the K point. But I just thought this is kind of like a vacancy order is actually a very interesting way to sort of tune symmetries in bulk materials and also give you flat bands. So this is maybe something that's worth looking at now that we have this construct of understanding where flat bands come from. Okay, so that's the first half, some examples. And then for the next half, I will tell you a little bit about having imaged these flat bands, how do we understand whether these flat bands participate in electronic orders in bulk materials. So I gave you some examples on the right-hand side, and all of these are systems that magnetically order. So before getting there, just to make a pitch for why this may be an interesting thing to look at, we've heard a lot about these compact localized states. They're actually, you can image them directly with STM. This is work from Berthold Deck's group at Hong Kong UST. And from STM DIDV maps, they can actually see if they tune their, so this is Kagome Kobo tin. if you tune your energy to be at the location of where the topological flat bands should live, they can see these compact localized states in the center, just like we have drawn theoretically. And if you go off away from those, you see the dispersive bands, which are on the edges of this Star of David shape, right? So these are real objects. You can see them, and we have seen efforts to mapping these onto these quantum critical phase diagrams and so on and so forth. So the question is, can these participate in giving rise to magnetic orders? So how do we actually learn about the nature of magnetic order from ARPA's perspective? I wanted just to show you how we can probe this question. What is the nature of a magnetic order? And then as we have all learned, there are different ways to understand magnetic order. And these are the two extreme limits. You can have a Stoner type itinerant origin of the magnetic order. And here, it's because the high density states, the Fermi level, that will spontaneously split to majority-minority states, and this would then give rise to the magnetic order phase, right? So give you the magnetization overall. What do you expect? You expect the spin splitting to happen right at the Curie temperature for this case. In the other limit, if you have a Heisenberg-like local moment picture, then the local moments themselves will persist well above the ordering temperature, which means that locally you will still have the difference between the spin majority and spin minority states, but they lose the long-range coherence. What that means is that on average, then you will you will have regions where this is spin up, with regions where this is spin down. So what you will see going across the ordering temperature is that the exchange spinning will still remain, but you just lose the spin polarization associated with each band. So you can see this is a very simple way from ARPA's perspective, to learn about how local or how itinerant the magnetic order is in a given system. You just ramp the temperature across the ordering temperature and see how much of this actually close, right? So people have used this, for example, to look at iron film, which many think is itinerant, but even for iron film, what you can see in this measurement is that while the spin polarization dies at the ordering temperature, at the Curie temperature, the exchange spinning actually only closes partially, and then they persist at a much higher temperature because of the persistence of the local moments, right? So you can by looking at how much of this exchange spinning closes to get a sense of where along this line the nature of the magnetic order is. So we can use this to study some of our systems to track what is the nature of magnetic order from this. So let me show you two contrasting examples. Iron tin, Stephen already talked about this. So this has been there's been previous work on single crystals, but it turns out that the ordering temperature for iron tin, so magnetic structure. Sorry, let me talk about magnetic structure. So the magnetic structure for iron tin is A-type AFM. So within each layer, the moments are ferro, and then they're anti-aligned in the stacking direction, right? So the ordering temperature is, it's a bit high, but not unreachable. And previously, there's been a lot of work on single crystals, but it turns out that it's very difficult to track the single crystals across this ordering temperature because the sample dies before you get there. So what do we do? So my postdoc, Zhengren, who was previously in Ilya Zalkovich's group, and he is expert in thin film growth. So he built an MBE chamber so that he can grow iron tin films and then directly measure the band structure. And it just turns out that these thin films, for some reason, are very robust. You can crank them through the ordering temperature down, and we can still look at the band dispersions and over the thermal cycle, so we can actually come to learn about the origin of the magnetic order in the system. So why can we even think about this picture for this material? So we did some DFT collaboration with Binghan Yan's group, and essentially you can think about the expected electronic structure evolution. Each layer is ferromagnetic, which means that it should split into spin majority, spin minority bands. So indeed, this is what's qualitatively captured in the DFT. So you can see that for the non-magnetic phase, the density states does have this large peak at the Fermi level, and that is this indeed maps to this topological flat bands from the Kagome lattice. And then in the AFM phase, you have a splitting of this peak, which if you look at the projected bands in the spin minority and spin majority states, they correspond to the topological flat bands, which are shifted up, and then the ones that are shifted down, right? So qualitatively, we can think about this picture and then ask the question, if we track through the ordering temperature, how much of this exchange splitting actually closes as a way to gauge the nature of the magnetic order here associated with the flat band. So first of all, where is the flat band? So we measure at the base temperature, lowest temperature we can measure, and in this large view, you can actually see this peak here around 1 eV below the Fermi level. That actually matches very well with the DFT predicted location of the spin majority flat band. So actually, you know, the DFT actually does a pretty good job for the low temperature phase. And so we can actually track this as a function of temperature. And we can find pieces of the momentum space where we can track the spin majority states, and then pieces where we can track the spin minority states. And as a function of temperature, indeed, the red bands shift up as expected, and the blue bands shift down as expected, right? This picture is qualitatively correct. But if you look at the energy axis, you realize that the amount that they shift is actually, in this case, is 20 millivolts, in this case, 200 millivolts, and that's labeled compared directly to the exchange splitting expected from DFT. And you can see that the amount of shift we actually see going across the ordering temperature is very small compared to the total exchange splitting expected. So immediately, this tells us that if you compare these two pictures, it's not an itinerant. It's not compatible with the itinerant ferromagnetic order, but it's actually much more closer to this end, the local moment picture, than the itinerant picture. So this is something we have learned from iron tin. Anyway, okay. That's the first one. I'm now going to shift gears and show you a contrasting example. And that is going back to this Clover bipartite lattice flat band seen in the iron germanium tellurium. So just a reminder, this is the flat band face. We can see that from these Clover lattice. And what we can do is we can now track these flat bands as a function of temperature. So the way we do that is we can take a cut here. Look at the vertical cut. This is the place where we only see the flat band. If you see one of these things, it has a hump. That's this flat band. Next hump, that's this flat band. And if we track this as a function of temperature, you can see that these two peaks merge together. And we also track, because this is a ferromagnet, we can actually look at the spin polarization now. And we did spin polarized ARPES. You can see that these two flat bands actually have the opposite spin polarization, right? So this picture that emerges is actually really close to what we see from this spin splitting into spin up, spin down bands across the ordering temperature. And this is in contrast to the case of iron tin in the previous example. So this is actually first time I think it's among all these metallic 2D van der Waals ferromagnets, you can see spin splitting of the bands across the ordering temperature. So this is the sort of another limit of this. In the remaining maybe 5 minutes or so, I'm going to show you the last example, which is actually, I think, is an interesting material that just recently came out. So this is structurally, this is isostructure to the cesium, vanadium 310, antimony 5 system that was discussed very well yesterday. And so instead of vanadium, we have chromium. And so this is the actually for this is all documented in this paper that may come out soon. So it turns out this system by itself, at ambient pressure, has a symmetry breaking transition around 55 Kelvin. Experimentally, it's been seen that there's additional superlattice peaks that appear that would suggest that this has a 4x1 charge density wave order that onsets across this ordering temperature. And there's also evidence that there is a magnetic transition associated with this temperature, which is seen, and this is magnetic susceptibility here, and then this is NMR shift here seen at the same temperature. So it suggests that there are actually two transitions, and there's a charge density wave order, and then an unknown magnetic transition that hasn't really yet been resolved yet. And what's really interesting is that under hydrostatic pressure, these density wave-like transitions are suppressed, and then at some point they split, and then when they're suppressed, you see the emergence of a superconducting dome, right? And then this is very reminiscent of all the unconventional superconductors that we have encountered, the nictide, the cuprates, heavy fermions, so on and so forth. And the other interesting thing is, especially after Eric's talk, is that when the authors measure the resistivity, and they look at this alpha, this is power law exponent, this is the large region of a non-Fermi liquid behavior, which seems to emanate from this, from here, right? This is starting to look like at least like a quantum critical point here in the dome, right? So, so this is actually, yeah, right. It's a promising material. Okay, so what have we done? What can we do? We can look at where the flat band is. So by DFT prediction, just to compare, the vanadium one has the Van Hoff singularities at the Fermi level, and then the chromium replacement of vanadium brings the flat band closer to the Fermi level. So this is by DFT. This is the location of the flat band. So when we do photo emission measurements, we can actually see the flat band near the Fermi level. For example, if you take a cut here near the gamma point, here, it's hard to see in the image, but if you do vertical cuts again, or these EDCs, you can see a peak everywhere hugging the Fermi level. Another way to see this is that, we can compare with the vanadium version. So in the vanadium version, for those of you who are familiar with the band structure, around the gamma point, there's an electron band. You can see it's very clear here, nothing there. But in the chromium version, if you take a line cut here, you actually see a peak appearing within this electron pocket. And why is that important is because if you look at the DFT calculation, this is the vanadium pocket, and the next band up is the topological, this is the Kagome flat band, which hybridizes with the vanadium electron pocket. So which suggests that here in this system, actually the flat band is much closer to the Fermi level even compared to the DFT calculation. And so we can further compare across the ordering temperature of 55 Kelvin, across this transition, and we can look at the position of the flat band. So as you go down from the red to blue, you can see the flat band actually shifts away from the Fermi level. We've done thermal cycling to check that this is a robust result. And we can track that this is roughly, give or take, something that onsets at least consistent largely with the ordering temperature, right? So it suggests that this flat band is at least responding, if not responsible, for the density wave orders here. And one may speculate, right, what is the effect of pressure? The pressure suppresses these density wave-like orders. Maybe that suppresses the shift so that there's a larger participation of the flat band when the superconducting dome appears, right? So as a bulk material, I think this is an interesting system to consider in the potential involvement of the Kagome flat bands in superconducting dome. But a lot more work needs to be done to really look at this relationship. Okay, I think that in terms of content, that's it. So I showed you some examples of how we understand the nature of the magnetic order in bulk materials. I hope sometime soon we can, as a community, look into this in the Moray systems as well. So some, I guess, summary. How do we find topological flat bands in bulk materials? We can think about 2D lattices, and then even going to 3D, which removes this interlayer coupling. And then we can think about systems where those compact localized states are not so much hybridized with the rest of the other bands. This will preserve the flatness of the flat band. And then also think about looking for systems that have partially filled 3D states that could potentially have stronger correlation effects that would further enhance the correlation in the system already produced by the topological flatband. And it considers things like vacancy ordering that can be used to switch on and off these flatbands, right? So in a triangle fashion, the base is how to construct these flatbands in bulk. And then there's a next layer up is thinking about, on top of constructing these flatband, we can also think about ways to tune the correlation effects for these bulk systems, and eventually, hopefully, connect them to the emergent orders that appear. So that's it. I just acknowledge I flashed many of their faces. I think my students, my group who are working on the topological flatband systems, and some of the recent graduates, Han and Jianwei is the one that works on ParaCore, and then the three guys who work on the Kagome system. Jisoo recently just moved back to Korea. Yucheng is the one that does also string, and also Zheng is the MBE guru in the group. And many collaborators that this is not a complete list. And then we're very thankful to all the collaborations with the synchrotrons beamline scientists over the years. Thank you.
Thank you for the nice talk. So you said that in some materials there's localized magnetism and some materials there's itinerant magnetism. I assume in most materials there's a mixture of two, right? And
right.
Is it possible like they affect each other, interact in some way?
Yes.
Did you use that in experiments, or just like the binary nature of magnetism?
You're certainly right. So I think it's never one or the other. I think it's very difficult to find in either limit. So I think most materials can probably just put them somewhere on that line. And the gauge that we have from measurement is just what portion of the exchange splitting is close by the time you reach the ordering temperature. I think that, at least for us, that's one way to plot them on this line between the itinerant limit and the local moment limit. Yeah.
Okay, thank you.
Thank you. Yes.
On the copper vanadium sulfide. So, in principle, there's a sort of Jahn-Teller active vanadium ion. So there's that degree of freedom. So what happens to it? And how does that impact your collaboration?
Yes, that's a good question. So I didn't mention there are two charge order temperatures below where we measure this. We haven't quite yet sorted out what is the.
Okay, so it does distort, and so the DFT calculation you're showing doesn't have the distortion. That's just sort of the cubic phase.
Yes,
okay.
right. Okay. We also calculated distortion for the CW phase, and it doesn't affect there's not too much distortion. We have to go a lot to distort to disrupt the flatband. Okay. Yeah, that's a good point. Yeah. Everybody's ready to go surfing.
All right. You guys can ask me. All right. So
Thank you. Thank you.